Okay, so last week I talked about the core effect at last, and actually at the time I get a little bit stuck for the argument why it is not possible to have a positive charge, and yeah, so I started recap the original Hall effect. So if we have a wire, the current is going from top to bottom, and then the external B field is going into the page. And in that case, you have, if you have a negative charge, which means that it should be going to bottom to top, which is opposite to the conventional current direction. So in that case, V cross B pointing to the left side, V cross B pointing to the left side, and in that case, the charge is negative, so FB point to the right side. And FE will point to the right side because this is negative, this is positive. So the E field point to the right side, and this is negative charge. So FE point to the left side. And actually, when there's more and more charge accumulated, then FE will become larger and larger. So then finally, the force will become equilibrium. And in that case, we can measure the voltage difference from the left side to the right side. So the argument here is that if it is a positive charge, which means it will have a same direction as the conventional current direction, which means VD pointing to the bottom. So V cross B point to the right side, V cross B point to the right side. And yeah, so the charge will start accumulate. The positive charge will start accumulate on the right side, and in that case, E field point to the right side. And in that case, we will have FE point to the right side, point to the left side, like this, and they will end up to be a equilibrium. So from the force equilibrium point of view, it doesn't really matter. But actually, the main difference is that if we assume the charge is negative, then for the voltage difference point of view, we will have a positive voltage on the left side and negative voltage on the right side. However, if we assume the charge to be positive, then we will have positive charge on the right side, negative charge on the left side. So they cannot happen at the same time. And from the experiment, actually the Hall effect experiment, we know that we should have a higher electric potential on the left side. So which means that we could not have a positive charge in this sense. Okay, so that's it. Okay, so let's move on to the next section. I suppose I'll finish chapter 28 today. Okay, so the next section is about circulating charge particle. So yeah, so now we assume that there is a B field pointing out of the page. So the B field here is out of the page. Let me choose, and so B field pointing out of the page. And of course, we assume the B field is uniform over the whole space. And now we assume that there is a particle. So G here means a generator to generate some particle, which is actually electron. So we have an electron gun, G here. So it will try to shoot out some electron in this direction. In this direction. Okay. So suppose this charge here at this moment, it has a velocity pointing, more or less upward. Okay, so in that case, you try to have V cross B. B is pointing out of the page, so V cross B is pointing to, this is V cross B in this direction. Okay, V cross B pointing to the outward, and actually it is a negative charge, so the FB should be pointing to the inside. to this point. Okay, so if it try to move, yeah, actually V points to this side, FB points to the left side, so it will actually move like that. Actually, it is the circular motion, what you have learned in high school, but at that time you assume that there is a mass here, and then for example, this is the Earth, this is the Moon, so the Moon will have something like the circular motion. Yeah, like that. Because if this electron at the next moment move to something like here, then the velocity will be pointing to point to this side, so that the force will be also pointing to the center of the circle. Okay. So in this case, yeah, we will have a circular motion of the electron. So it says applying the Newton's second law to the circular motion use this equation. Actually, it is like F equals ma. Newton's second law of motion is nothing but F equals ma. So this is the Lorentz force. F equals ma. So this is the Lorentz force, and m. This is m, and a will be v squared over r. Yeah, I suppose you should have learned it in high school. Like that. So in that case, v and v can be cancelled. And we finally found that we move r to the left side and move qb to the right side. So we will find that r equals mv over qb, mv over qb. So this is the radius of the circular motion. So this is m is a constant because electron have a constant mass. If you don't consider the relativistic effect, yeah. So this is v, and then q is the charge for electron, which is actually the elementary charge, and then the B field is what you given. You assume it is uniform. So which means that R is proportional. R is proportional to velocity. Oh, R is proportional to the velocity, which means that if the velocity, instantaneous velocity is larger, then the radius will also be larger. Okay, so this is simple, I think. Okay, so let's take a look at a sample problem. So it says, an electron with a kinetic energy of a 22.5 eV move into a region of a uniform magnetic field. So this magnetic field is pointing upward. Yeah, with this magnitude, the angle between the direction of B and the velocity and the electron's velocity is 65.5 degrees, so that they are not perpendicular to each other. So what is the pitch of the helix path taken by the electron? So yeah, so V is this one. So this phi is 65.5 degrees. So this phi is 65.5 degrees. Okay. So actually, here we assume that this V is perpendicular to the B field. B field is pointing out of the page. It is perpendicular because V is on this plane. So they are perpendicular. So in that case, we need to decompose this V into two directions. This one is perpendicular to the B field's plane. Perpendicular to the B field's plane between this one. Or you can say this component is parallel to the B field, And the other component is, of course, V perpendicular to the B field. Okay, so we decompose it in two ways. So in that case, the velocity of this component will make the electron. Yeah, I think it is electron. Yeah, electron to have circular motion on this plane. However, it also has a component which is parallel to the B field, which means that due to this velocity, this electron will move in this direction, due to V parallel, like that. So when these two velocity add together, it will be somehow like having helix motion, helical path. So it asks, what is the pitch? Pitch is actually like, so this is like a helix. So if you try to find the distance between the two adjacent helix, so this distance is called a pitch. Or at any point you draw a line which is parallel to the B field, then for the adjacent intersecting point, then it is the distance of pitch. This is the pitch. Okay. So first of all, we would like to find what is V, because you are only given the kinetic energy. So we probably need to use a V equals square root of 2k over m. Square root 2k over m. Because k is 1/2 of mv squared. Okay, so here we have 2 times 22.5 times 1.6 times 10 to minus 19. Because this is EV, you need to convert it back to joule. And then all over m. The mass of the electron is 9.11 times 10 to minus 31. And then the whole term take the square root. Okay, like this. So it is 2.81 times 10 to the 6th power meter per second. Okay, so yeah, so this is the velocity. So yeah. Okay, so actually, this distance will be like a period of the electron taking the circular motion, then in this direction. Pitch will be like V parallel times the period of the circular motion. So actually, just now we know that here we have R equals mv over qv. So actually the period of this circular motion will be something like 2 pi r over v, something like that. 2 pi r is the circumference of a circle, and then divided by the instantaneous velocity. So 2 pi over v times r is here mv over qb. So we have mv over qb. So v and v can be cancelled. We have a 2 pi m over qb. Yeah. Okay, so this is the period. So the pitch here will be V parallel times T, which is V here, V parallel. So this is phi, this is V. This is the adjacent side, so it is cosine, V cosine phi, and then times 2 pi m over qb. Okay, so this is 2.81 times, 2.81 times 10 to the 6th power, and then cosine of 65.5 degree, and then times 2 pi times the electron is 9.11 times 10 to minus 31, okay, all over 1.6 times 10 to minus 19 times 4.55 times 10 to minus 4. So this is the magnitude of the B field. Okay, so finally we have 0.0916 meter, or you can write it as a 9.16 centimeter. Okay, so this is the pitch here. The pitch here. Okay, any questions? No questions. Okay, so next we have another sample problem. So here it says the essential of the mass spectrometer, 频谱仪 which can be used to measure the mass of an ion, mass of an ion. So an ion of the mass to be measured, and charge Q is produced in the source S. Initially, stationary ion is accelerated by the electric field due to a potential difference V. So as you can see at this point, at this part, so for this part you have we have uniform B field, and for this part we have electric field. We have E field here, which is like this. E field, we have E field like that. Okay, so in that case, if you have an ion here, which is a charged particle in the E field, so it will accelerate. It will accelerate. And then starting from here to there, then it will have more potential energy. So the ion leaves S, which is the source, and enter a separate chamber in which uniform magnetic field is perpendicular to the path of the ion. So like this, we have a B field pointing out of the page. So a Y detector line at the bottom wall of the chamber and cause the ion to move in a semicircle, thus strike the detector. So originally, if the B field is large enough, then it will have circular motion. But yeah, it will go here for semicircle, and then until here it hit the detector. So we can see the position where it hit the detector. So we know the radius of this circular motion. Okay, the idea is somehow like that. And the cause of the ion to move the semicircle thus strike the detector. Suppose that B, V, and Q like this strike the detector at the point that lie as 1.6 blah 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 meter. So what is the mass of the ion in atomic unit? So it divides by this mass, which is something like a proton, a proton's mass, like this. Okay. So here we can consider like delta K plus delta U equals 0, which means it is mechanical energy is conserved, the conservation of mechanical energy. So the change of kinetic energy plus the change of the potential energy will be 0 for this part. So initially the kinetic energy is 0, and then it will accelerate. So the delta K will be nothing but half of mv squared. Half of mv squared is at this point. We will have K at this point, and here Ki equals 0. This is Kf. So this is m half of mv squared, or we assume the velocity here is v, something like that. So initially, there will be electric potential energy because we have electric potential V here. So the electric potential energy here is Q times V. If you still remember, U equals QV, something like that. So at the final point, there will not be any electric potential energy anymore. So it will be like minus QV. So here, UI is QV, and then UF here is 0. So delta U will be negative QV, like this. Okay, so here we can have V equals square root of 2QV all over M. Okay. So here we have a V equals square root of 2QV over M here. Okay. So yeah. So actually we should have R equals MV over QB. Now we can substitute V into here. So we have M over QB times square root of 2QV all over M. So okay, so part of it can be cancelled. So we have here square root of M. So we should have square root of M here. And then Q, square root of Q. We should have square root of Q here. Something like that. Okay. So we will have 1 over B and then square root of 2mv. This is capital V, which refer to the potential, electric potential here, all over Q. Yeah. And of course, what we know is actually x. X is the diameter. X is the diameter. So x will be 2 times of the radius. 2 times of the radius. So we will have x to be 2r, which is 2 over b times square root of 2mv all over q. So finally, we would like to find the mass of this electron. So we can do some algebra. So m equals 8v. You can slightly do some algebra, which is like 8mv and then b square q, and then take the square root like this, and then you square both sides, so you will have x square b square q over 8v like this. Yeah. Now we can substitute the number into here, so we have a 1.6254 quantity square times B is 80 millitesla, so 80 times 10 to the minus third power and then square, and then times Q is 1.6022 times 10 to the minus 9, so which is quite large, and then 8 times V is 1000 volts. Okay, so this is 3.3 863 times 10 to minus 25 kilogram. But actually it asks you to represent it in the atomic unit. So you divide it by 1.66 0.05 times 10 to minus 27. So this is 203.93 U. Okay. So actually, if you try to check the best number of the from the periodic table, you will know what should be this element, including both the number of proton and neutron. And also, this is almost like a 100E, 100E, around 100E. Okay. So, any questions? No questions. Move on. So here we talk about the cyclotron. Cyclotron. In Chinese, it is called 回旋加速器。回旋加速器。Okay. So this is called a cyclotron, which is a short of the particle accelerator. So it can accelerate some charged particle. And yeah, so it says here, it's the top view from the region of the cyclotron in which the particle, say proton, circulate. So the proton or the charged particle can go like this, go like this, go like this. So the two hollow D-shaped object, each open on its straight edge, are made of copper. So you can see here there is two D shape. So half of it on the left, half of it on the right, and then there is a tiny gap in between. And this is important. I will let you know one page later. So yeah, so it will generate an alternative E field between this gap. So for some time the E field here, sometimes the E field point to the right side, and then sometimes the E field point to the left side. Alternatively, and actually periodically, then yeah, so in that case, it will try to accelerate the charged particle. So the electric side of the D are alternative, so that the electric field in the gap alternating in direction. Well, and in the D shape, there will be magnetic field. You can see some green dot, which means the B field is uniformly and also pointing out of the page. So the key to the operation of the cyclotron is that the frequency f which the proton circulate in the magnetic field, blah blah blah, and it will be equal to this one. So just now I already tells you that the t will be 2 pi r over v. So f is, which is 1 over t. So this frequency is the reciprocal of the period. So you can just check that. Or you can just substitute r here. You can find t, capital T, and then you can find f to be like this. Okay, so what's the trick here? Because if we don't have this gap, and if we have the uniform B field and then the charged particle going into this region, then it will have circular motion. So the punchline here is that we try to separate this circle a bit, and then we try to make this charged particle here to accelerate from time to time. Then the velocity will become higher and higher. And if you still remember, I've mentioned that if you still remember, R equals mv q over qb. So I just mentioned that R is proportional to the velocity. So if the charged particle become faster and faster, then the radius will also become larger and larger. So in that case, you can see it will have circular motion and then accelerate, circular motion, accelerate, and then so on and so forth, and then it will become faster and faster, and then finally shoot out. So if actually I can slightly draw a larger figure so that you can know what it's like. So here we assume that the gap here is like this, and then this is the source point S, okay, here. So we try to shoot out. So from the period when the charged particle going to the left side, just say if it is positive charge, then the E field also pointed to the left side, with the same direction. So then it will try to accelerate for this distance. Okay, so here in this region, it will not have E field anymore. So it will stop accelerating, and then in that case there will be the initial velocity v here. So that it will, maybe let's say this is v1. So it will have circular motion for this region like this. Okay, so up to here, there is no B field anymore, so that it will go in this direction. And at this time, like this direction. Okay, so in this case, we will alternate the direction of the E field to the right side. So in that case, the charged particle will keep on accelerating at this region. If we just keep this E field pointing to the left side, then it will decelerate. Then yes, then you won't have a particle accelerator. Maybe you just like going from here to there, and then going here, and then stop here, and then going back, something like that, and it will stop accelerating. So actually the point here is to control the E field precisely, and then in that case it will have another circular motion. And here of course V2 is larger than V1, so it will have a larger radius. And going back to here, then we need to change it back to so we will have the particle here, and then going in this direction. And of course we need to change it back to E field pointing to the left side, and then we will have V3 here, and then V3 is larger than V2, so it has a larger radius like this. So it will keep on doing this procedure until it will shoot out somewhere. Okay, so the mechanism of the cyclotron is like that. Okay, so it says the energy for this particle accelerator is small, which is like less than 50 mega EV. So you just keep this number in mind. Yeah. Actually, you don't need to memorize it. I just talk about some story here. So it says the energy of the particle will be small, because in this case we need to have a very large disk here, and then we need to generate the B field over the whole area. So it will consume power, because if you still remember, B field, if you need to generate B field, it needs energy. So if you need to generate the uniform B field in a large area, then you need to have very large energy to do that. So that's why it cannot have a large energy for that, because you can see here the R also inversely proportional to the B field, which means that if the B field is not large enough, then this disk needs to be very, very large. Okay. So another way of doing particle acceleration is called the Singletron. So in Chinese, it is called 同步加速器. Okay, so actually we will not go deep into this one. But actually the main difference between the synchrotron and the cyclotron is that the synchrotron will be like you only have a something like a ring here, and then you try to manipulate the B field. Try to manipulate the B field so that the control will be more complicated, but you only need to generate the B field inside this ring, so that you don't need so much energy to do so. So the magnitude, B field, and the oscillating frequency, instead of having fixed value in the conventional one. So for the previous one, we have fixed value of B field and the fixed F oscillation are made to vary with during the accelerating cycle. So this is done properly. When this is done properly, so you need to have a precise control, so that you need to manipulate the direction of the manipulate the magnitude of the B field, because you can imagine R equals mv over qb, so that here you need to keep R to be constant because you only have a ring here. So that if V becomes larger, you need to, at the same time, you need to increase the B field for the same portion. Otherwise, the R will change, and then the electron will be something like going this way hitting the wall, or going that way hitting the inner wall. So you need to control the B field precisely. Yeah. So the frequency of the circulating proton remain in step with the oscillating at all time, and so the proton following a circular, not a spiral path. Thus the magnet needs extend only along a circular path, not over something like this. So you can imagine this is 4 times 10 to 6 meter square. So if you just take the square root of it, it will be like 2 kilometer. And of course you say pi r square. Pi r square is the area of the circle. So maybe you just divide it by pi, so which is around 1 times 10 to the 6, and then take the square root will be 1 kilometer. So which means that the radius of this synchrotron will be 1 kilometer. Okay, so the circular path, however, still must be large if high energy are to be achieved. So it says the beam is then injected into So I actually find it on the Wikipedia. It says the beam is then injected to the proton synchrotron booster (PSB), which accelerate the proton to 1.4 giga eV. So compare with this one, this is less than 50 mega eV, and this one is a 1.4 giga eV, followed by the proton synchrotron, which push the beam to 25 giga eV. So this energy is 25. This is 50 mega. So which is 500 times larger. Okay. Okay. So here we have another sample problem here. Okay. So here it says, suppose a cyclotron is operate at an oscillating frequency of 12 megahertz and has a radius R to be 53 centimeter. What is the magnitude of the magnetic field need for deuteratron? Deuteratron means it has one proton and one neutron. One proton and one neutron. So it is called 重氢 重氢. Or if you learn chemistry, it is called like this. If I remember correctly, because my chemistry is not good. Okay, so yeah, so which means it has one proton and one neutron, which means it is a isotope of the hydrogen, because for hydrogen it only has one proton, but yeah, it has one proton and one neutron, which means it is an isotope of the hydrogen. So to be accelerated in the cyclotron, the deuteron mass is 2 times of the proton. Okay, here, let's see. So we have B equals, let's see here. Here we have F oscillator. Let's copy it. Yeah. Here we have F oscillator to be QB over 2 pi m. So we can have B equals 2 pi m times F oscillator, 2 pi m times F oscillator over Q. Okay. Okay. So we can plug in the values. 2 times 3.15 times the mass is 3.34 times 10 to minus 27th, and then times F oscillator is 12 megahertz, 12 times 10 to the 6th power, all over Q is 1.6, because it is one proton, one neutron, so it has one elementary charge. So it is 1.57 Tesla. Okay, so this is the magnitude of the B field. Okay, so for part B, what is the resulting kinetic energy of the deuteron? So we have V equals RQB over M, because we have R equals MV over QB, if you still remember. Yeah, so this is 0.53 times 1.6 times 10 to minus 19 times 1.57, all over M is 3.34 times 10 to minus 27. So this number is 3.99 times 10 to the 7 meter per second. So this speed is quite fast, which is around more than a tenth of the speed of light. Yeah, I suppose you know the speed of light will be the speed of light will be 3 times 10 to the 8th power meter per second. Yeah, meter per second. Usually, if we remember 3 times 10 to the 8th meter per second is enough. But when you learn the relativity, yeah, you know the number will be 2.998 times 10 to the 8th meter per second. Okay, so this is the velocity, and the kinetic energy will be half of mv squared. Actually, we will probably need to consider the relativistic effect, but of course now you don't know. We will cover that part in chapter 37 in this semester. Okay, so this is half times 3.34 times 10 to minus 27th, and then times 3.99 times 10 to the 7th power quantity squared. So this is 2.7 times 10 to minus 12 joule, or you can represent it as a 17 mega eV by dividing this number by E. Dividing this number by E, then you get the energy in EV. So this is of course smaller than 50 mega eV as mentioned before. Of course, it is just to let you know what will be the practical number. Sometimes the sample problem will be very easy. You just need to plug in some number and then calculate it. And then the point here is to let you have some idea of the practical values, because yeah, in physics point of view, it is important. Okay, so let's have a 10 minutes break.